Okie dokie. Yes, this one. Alrighty, so today, while my tablet is updating, I figured we'd start with taking a look at some chemical reactions. So I'm just looking at our textbook here. We're going to look at a couple of reactions, and we're going to see what's kind of happening in all of them. And so we're going to use this a little bit later. We're going to still start off with kind of talking about states of matter, but we're going to see kind of evidence that we see these different states of matter happening. So let's take a look at this first one. We see two clear liquids, and yet when we mix them together, we get this white solid. Notice it's actually a solid, it's just very small particles. That's why it seems to be kind of creamy or something, but that's how we would know there's a precipitate in there. A solid is usually indicated by some sort of cloudiness. It's not necessarily big chunks. So these are actually the kind of very fine particulates that if we were to let this settle out over time, we would be able to see that kind of separate. All right, we have a liquid forming reaction next. Before I start this, liquid forming reactions always produce a lot of heat. So we can see that with this thermometer here. So you see it's about 22-ish degrees. You mix them together, we can see all this kind of steam happening, and you can see the temperature just going crazy. Now it's at 50 something, almost 60, thereabouts. So there's definitely a lot of temperature change there. So that would be another bit of evidence that something is happening. So we can't necessarily directly see water being formed, but we can see it through other means, such as the temperature. Here's one that we've all done back in our, elementary school days. This is one that produces a gas, which we can see by vigorous bubbling here. So that one is essentially your vinegar and baking soda type one. Let's go ahead and watch that. Just so you can see here all these bubbles that are forming. That's rapid. This is real time. This is, a very quick reaction that takes place. These double displacement reactions that we're all seeing here are all very, very quick. This next one we're going to see is a single replacement. We have a strip of copper wire, and I'm pouring in some silver nitrate solution. And we're going to time lapse this, so it's going to be a little bit interesting here. So let's see. Let's look at this copper wire. We can see clearly it's not exactly copper wire anymore. We have small little crystals of silver metal forming on this, and they're falling off. This is gravity. And it looks like a Christmas ornament or something. Notice also the solution around it is turning blue. Copper 2 ions are actually blue. And so that's what we can kind of see here. So you can see all that silver metal back there. Let's see it nice and kind of up close here. It was just kind of on the surface of that copper. And then if we take a look at the solution, we can see very nicely that it is blue, where it used to be clear. So that's kind of our evidence that we had reactions happening. We had the silver forming, and then we saw the rest of the solution turning blue. All right, tablet is almost done. Do we have any fun other videos on this? Probably not. So tablet's at 95%, but that's okay. We can go ahead and swap back. Alrighty. So we're going to go ahead and continue on with our states of matter. There we go. Tablet has updated. It is now restarting itself. Do we have any questions, by the way, from anything we did yesterday? I guess I can also talk about the lab project. So that has been posted on Canvas for you guys. So you should definitely take a look at that. You're going to want to, if you want me to choose your groups, I'm going to do that on Friday. No. Those were just videos, Ali. So nothing to write down. And if you don't have the textbook, you can probably find tons of videos on YouTube of various types of reactions if you really wanted. But yeah, just evidence. Okay, so back to lab thing. I'm going to randomize groups on Friday. If you tell me before Friday that you would like to work with a particular person or a couple of people, I'm happy to accommodate that. If any of you have, started talking with each other since class began, I'm happy to work that out with you guys. On Friday, I will otherwise randomize the groups, so you'll be kind of stuck with those people until the end of the semester for your lab project. So make sure you go ahead and take a look at that. Ask me any questions you have. Essentially, you're going to be looking at various videos of techniques and equipment that's used in the chemistry lab. And you're going to be designing an experiment to solve a problem. So whatever that problem would happen to be, if it's, hey, prove that something is this, or, figure out what substance this is, or, find a way to figure out the concentration of something in this solution. Lots of different things that could be possible. So I'll be assigning topics next week. So this first week you'll be able to kind of meet your groups and kind of decide what you want to do, like how you want to meet, if you want to use Zoom, if you want to use Discord, if you want to use just Canvas messaging, if you want to text each other, whatever, figuring that out. So that will be due a little over a month from now, December 6th. And that is going to be something you'll submit on Canvas, and you will also individually submit kind of a report on how your group functioned, like who did what parts of the thing, like who wrote what, as well as kind of if there was one person who just refused to do anything and was just a grumpy, I blah blah blah, I don't like this, you can let me know there as well. So let's see. Actually, I guess we can go over this now while the tablet is restarting. I also put up your Proctorio quiz, so you can go ahead and see that as well. So you can practice that, so you're going to be all set for the exam day. Okay, so let's see. Let me try and capture another window here. Yes, this one. Okay. So here is our lab kind of guidelines. Oh, I see we're kind of to the side, aren't we? Let's see if we can't fix that. What if I do this? Would that make it better? Yeah. Okay. Cool. So you are going to be working in groups. So if you do have people you want to work with, let me know. And you're going to be designing an experiment. You're going to be given some sample laboratory protocols that you're going to kind of use to model yours off of. So you're going to see they all have an introduction, including, say, if we're talking about precipitation reactions or whatever, there's a bit of information about that. Maybe some example chemical equations. Then you're going to have a detailed procedure showing exactly what you're going to be doing. And so that kind of comes with two kind of parts there. So your experiment may be qualitative or quantitative. Quantitative means you're doing some sort of calculation. You're figuring out the mass percent of something. You're figuring out the molar mass of something, whatever, something that is involving calculations and numbers. You're going to want to include sample calculations and all that sort of thing. If yours is the other one, the qualitative one, that's involving, do I have this thing in here, or what is this substance? That one is not necessarily going to have a lot of math, but you will want to put, expected reactions or something, some sort of how you would figure out what this would be. And then, of course, you'll include any references that you used. I'm totally okay with you using Wikipedia as a reference. Science ones are usually not problematic because nobody goes in and changes those, but also the Wikipedia team is pretty solid at making sure nobody messes with them. All right, and then so everybody's going to submit an identical experiment, everyone in the group, and then they're also going to submit a kind of how your group functioned little thing. So that will be posted later. Alrighty, so here's how you're going to be graded on that. So of course your accuracy is going to be kind of the most important part. You know, would your chemical reactions help prove this particular thing? You know, does your math make sense? How feasible your experiment is? You know, are you going to, you know, go from A to B while also going through, you know, C, D, E, F, G, H, I, J, K, L? You know, how unnecessary are some of the steps? Is there a much better way you could have done this? You know, that sort of thing. Safety information, of course. There are videos and kind of a place you can look up safety information based on whatever chemicals you want to use. Your contributions to the group, and then, of course, your thoroughness in your explanations. So I don't really care about your grammar so long as I can understand what you're trying to say. So that should not be something that you should worry about. And just as a little incentive here, whichever one I find to be the best experiment will get some extra credit as well. Okie dokie. So, with that in mind, you know, you guys are, of course, free to contact me. And I do suggest someone from your group at least, you know, pop in every week or so maybe, and just let me know how things are going. If you guys are stuck, like, hey, how would I, you know, figure out how much chloride I have in this or something, you know, just something, you know, general questions I'm happy to answer. All right, the tablet is finally loaded. That looked like a lab. Yes, Kenji, you're going to want... Sorry, I couldn't see the chat with the Word document blocking everything. Kenji, yes, you're going to want to make sure you do that. There are instructions. All you have to do is install one plugin, and then after that, you'll be all set. So everything in that email should have all of the information. Okay, good news. The tablet is deciding not to connect now. So in the meantime, we can answer more questions. We had some demonstrations, Maya. So just a couple of videos from the textbook that we were watching just as evidence. Okay, I'm going to try restarting this tablet again. We'll see. Updates are always problematic, you know, and it's like 10 minutes beforehand, I'm going to decide to update on you. Ha ha ha. Okay, so we'll give that, you know, 30 seconds or whatever, how long it takes to restart. Alrighty, so do we have any other questions about the lab? 4 people, Kenji. It's the very first sentence. Okay. So yeah, if there's, you know, if you know 3 other people you want to work with, that's fine. If you know 1 person that you want to work with, no worry, Kenji. You know, just let me know, and whatever way you want to do it. If you want to send me an email, if you want to message me on Discord, doesn't matter. Just let me know somehow, and I'll make it work. Okay, tablet has restarted. Any other questions on the lab project, by the way? Your topics will be assigned next week, so you'll have, of course, some idea of what the heck you... No, you're not gonna perform it. You're designing it. So it is all on paper. There is no actual physical... I mean, how would you get the chemicals needed, right? Like, That would not be something that you guys would be able to do. All right, so I'm trying this. Aha, we've done it. Okay. Hooray, it's finally, yeah, hush, mister. Yeah, unfortunately, like, for safety considerations, you're not going to be able to do them yourselves. However, if you're still taking chemistry and you want to do your experiment by the time we get actually back on campus, that's okay. Then we can do it there. Yeah, I mean, I'm sure you can get away with it. I mean, you're welcome to do it if you want, but you maybe clear it by me just to make sure that anything you're doing is not producing any toxic gases or whatever. So, alrighty, so back to states of matter. Now that the tablet has figured out its stuff. Yeah, so this is exactly it. It's that would-be type scenario. You're going to write a procedure and design your experiment. And so what's interesting about this is also, you kind of have a lot of freedom. A lot of these things, there's going to be a bunch of different ways you could try and approach the problem, and a lot of them will work. So, it's completely up to you as what you guys like to think about. So, cool. Alrighty, so we had solid yesterday. Those are going to be our insoluble compounds. We saw that we had liquid as well. That was going to be our water and bromine. And technically also, if you were to see mercury by itself, it is also a liquid. Oh, wait a second. I also can't see anything. It's a stupid thing. Why are you not loading? Okay. Let me try disconnecting it and reconnecting it then. Yeah, because I just see a blank screen as well. Isn't that fun? All right, let me close this again and we'll see what we can do. It's always funny. It's always your class that I have the tablet troubles in. I guess that's the that's the detriment of going first, I guess. We get through all of it, and then 111 is fine in the later in the morning. Okay, it says it's connecting now. Let's see what's gonna happen. Okay, hooray! Now we can see what I wrote. So the same thing that we kind of ended with yesterday. So, okay, now we can continue. Alrighty, we also talked about our aqueous things. Those are going to be soluble compounds. If water is present, which means a reactant is aqueous. So remember, these are all for products. Your reactants would be given to you, what their state of matter is. Okay, so all this stuff we did yesterday, we're going to practice that, of course, in a little bit, but let's talk about the last state. So this would be the gas one, and we're going to have a few gases here. These are the 4 gases that we're going to see. That will result from replacement reactions. So we're going to see that this one, hydrogen sulfide, would just be something like, for example, standard double displacement. This one would be a gas. So H2S will just bubble out of solution. That is your rotten egg smell compound, hydrogen sulfide. Very stinky. you would know right away if you produce this, because you would not only see bubbles, but you would then also have this really nasty smell in the air. So you would know that right away. So anytime you're producing hydrogen sulfide, it will be a gas. The other three gases, these three here, don't typically form directly, but in fact they form from unstable compounds. We're going to see if you form, well, that's really ugly, ammonium hydroxide, that will immediately break down into water and ammonia. And this is another one you would be able to smell. Ammonia is a cleaning agent. You may have it in your house. Really stinks. It's quite a pungent smell. You would know it right away. This one typically doesn't bubble because ammonia, it being a very polar compound, doesn't kind of form these bubbles in water because it's pretty polar. All right, if you form carbonic acid, that one will also break down, and you'll get your CO2. We're going to look at reactions that would do these, by the way. And same thing if you were to make sulfuric acid, that's where you would get your sulfur dioxide. That's another smelly gas. This one's really, really quite toxic. So that's one you would definitely want to do in a fume hood. You will learn what a fume hood is in those equipment videos on Canvas. Okay, so if we take a look at a reaction that might produce one of these, say for example, we can take our vinegar and baking soda, we're going to see, of course, the ions there. We're going to pair them off. So we would make these two compounds. Notice here we have that carbonic acid. If we ever form carbonic acid, we are not going to leave it as carbonic acid. We are going to go ahead and put it as the water and carbon dioxide. We saw this, right, in that video at the start. We saw that if we mixed our vinegar and baking soda, we get bubbles. Neither carbonic acid nor sodium acetate is a gas, but we saw those bubbles came out immediately, and they were pretty much all done within a matter of seconds. Excuse me. So we definitely have evidence that we see the gas there. So this carbonic acid breaks down right away. It's also the compound that's in carbonated beverages that is breaking down, producing these bubbles. So anytime we produce one of these three, ammonium hydroxide, carbonic acid, or sulfuric acid, we're going to go ahead and break those down into water and their respective gases. Okay? Let's do another example, perhaps. Let's take ammonium chloride and lithium hydroxide. Looking at the ions, that's what we've got. So we're going to make ammonium hydroxide and lithium chloride. And so we're going to want to, again, Remember that this is one of our gas-forming compounds. So we would want to put the ammonia and the water. Of course, our lithium chloride would be aqueous. All right, so for our gases, if you form H2S, hydrogen sulfide, or any of those three compounds, ammonium hydroxide, carbonic acid, or sulfuric acid, you've got to break those down and form a gas. All right? So just four, I guess, to remember. Shall we do some practice then? What shall we do? I guess I should give you states of matter, huh? Since that is the whole point of this. Okay, let's do one more. I guess I should do a fourth one because I didn't get as many as I wanted in there. What shall we do? How about... Oops. Ba-ba-ba. Okay. Let's see if I have enough room. Suffice to say, your reactants would be aqueous on the bottom. Actually, you guys have probably had enough on the top. You can see it all. Alrighty. So someone tell me the products of these reactions as well as their states of matter. That is what we'll do. Again, with this, you'll have plenty of example reactions you can go over. You're welcome to put the chemical equations. You can just, if you take a look at that when that's balancing, you can just kind of write them on a separate page or something, just the reactants, and then come back later and try and predict the products with their states of matter. And then you can balance them, and then you can identify them, and then you can do, all this fun stuff with them. Where did you get carbon dioxide and water from? You have the silver chloride you have is correct. Let's go ahead and look at these. What's the product we would get if we took the H and the acetate together. That one should just be acetic acid. So I think you were thinking of carbonic acid. You were thinking of this one, but that is not the one that's being produced here. Carbonic acid you would get if we used silver carbonate or silver bicarbonate or something. You might get this, but probably, I mean, the acetic acid is not the same. Does that make sense, Lamonda? Okay, cool. Alrighty, so let's look at the sulfuric acid and potassium hydroxide now. What are we going to get from this reaction? Take a look at the ions. What are we going to make here? Yep, it is. So that will be one of them. Mm-hmm. And what's the state of oh, you got it. Aqueous, yes. Very nice. Ah, Sherry did the aqueous part. Yeah. So potassium sulfate should definitely be soluble. So hooray, awesome. Just technically, if we wanted to balance this, by the way, this is what we would get. I didn't ask you to balance them this time, so don't worry. Next one, we've been doing so many double displacements, I threw in a single replacement there as well. Let me see. There we go. Yes, this will work. This for you guys. This. Alrighty, so I've put something up for you guys. You can see it's just a periodic table online. How do we know that? Because it has potassium and it has sulfate. So for both reasons, it's going to be aqueous. So if we go back to our solubility rules, just save this real quick. Or no, that's not what I need to do. If we go back to our solubility rules, I guess we kind of touched on them yesterday. Anything with potassium would always be soluble, and also sulfates would be soluble except with a few things. So for those two reasons, I mean either one would be sufficient, but we have both. So okay, let's go back to this. Oh, so neither of your answers is correct, but you have somewhat components of them that are. So chlorine is metal or non-metal? It's a non-metal, right? So in NaBr, which one is the non-metal? In sodium bromide. Indeed. So the one that's going to be replaced, therefore, is bromine, right? Non-metals replace other non-metals. Metals replace other metals. So we're definitely going to get the sodium chloride there. But the other one that we're going to get is bromine by itself. Remember, bromine also occurs, just like every other halogen, as a diatomic species, so it's always Br2. And then, so remember, bromine is going to be one of our liquids as well. If we forget this, I did just put something for you guys. If we go to here, if you want to look at a particular element by itself, we can look on this lovely shiny periodic table. Lo and behold, bromine is got letters of blue. Yeah, exactly. Yeah. So blue ones, it's going to tell us right here, are going to be liquids. So if you're looking at an element by itself, anything that's in a black lettering will be solid. If it's blue, which is bromine and mercury, that's a liquid. And then we, of course, have our gases in red here. Okay, so you can use this as a reference as well. Most periodic tables will also include this information. This is just one that is nice and shiny and pretty, so why not? Okay. Cool. Alrighty. Tough one. I'm just going to also write these down. These 7 elements in purple always come as pairs. This information is on that like summary of ions sheet. They are always diatomic by themselves. By themselves means they're not part of a compound. They're just occurring as 2. Like oxygen, the oxygen that we're breathing is O2, the nitrogen in the air is N2, just by themselves. They will always be these diatomic ones. Okay, let's go to our last reaction, back to double displacement. Yeah, so this stuff is tough. It takes a lot of practice. So you have hundreds of practice problems. You are more than welcome to do them as many times as you like. How fun. Alright, so since we're back to double displacement, we can look at our ions again. Almost Sherry. So very nice work on the nitrate there. Perfect. But your HSO3 is not quite correct. So technically, you would get this if you were just doing the switch, but this one is going to be one of our special ones that breaks apart. So you have noticed there is a gas there, so that's good. So what you should do then instead is actually break it apart. So instead of that, let's go ahead and erase it. We would get water plus SO2. And that SO2 would be a gas. So technically, these both came from the H2SO3. It just broke apart. It's just an unstable compound, so it will just break apart and form that gas. Yep, tricky. That would be these 3 right here in blue. If ever you have one of these, you're going to break it apart. So anytime you produce one of these 3, you're going to want to go ahead and instead write the other 2 products. Of course. Yeah. So in this case, we did the last one. So we're going to break it down into water and SO2. Yep, that's exactly right. So if you can imagine, we're taking off 2 hydrogens and an oxygen, and then we're left with SO2. Same thing with the carbonic acid. Actually, all of these, you can kind of see we're just taking away a water. And whatever's left is going to be your gas. Alrighty. So yes, you'll want to practice these because they will haunt you forever. Okay. So in that case, let's go ahead and look at things in a little more detail. Many components of a chemical reaction How many balances this change? So, Lamanda, if that's a good question. If you do end up having something like that, it's best to balance it as H2SO3 first. If you balance the H2SO3 and it's got a coefficient of 1, you're going to get 1 water, 1 SO2. If your sulfuric acid has a coefficient of 2, you're going to then get 2 waters and 2 SO2s. If your H2SO3 has a coefficient of 3, you're going to get 3 waters, 3 SO2s. So that is how you would do that. That would be, I think, the easiest way to balance that. For this other one, the only balancing we need, though, is that. After that, everything else is okay. Let's see the other one. Yeah, technically, we're going to need 2 of those. But, yeah. Okay. So it turns out that a bunch of the components of a reaction may not actually be participating at all in the chemical reaction, and they're just kind of there to charge balance things. And we call them spectators, or more commonly spectator ions. We can see them in, or let's say identify them, in what is called a complete Ionic equation. So if we take a look at one of those, what was it? So we saw this became sorry, I had no room for the sodium acetate there. It's kind of shoved off at the top. If we take a look, so this is a standard chemical equation that we have here. It's called a molecular equation. If we break all aqueous species into their ions, let's take a look at what that would be. So this is now, we kind of use this as a way to figure out our double displacement products, but we can actually do it in an equation form. So if we break our acetic acid up, and if we break our sodium bicarbonate up, I'm going to leave the water alone and the carbon dioxide alone, because those are not aqueous. Sorry, I've kind of run out of room here. So remember, aqueous means things are dissolved in water. And we saw that when things dissolve in water, the ions split apart. Right? We saw that when we talked about solutions. What we want to do is we can look, is anything the same is any component here the same on both sides, meaning it's exactly identical. So if we just go from left to right, do we have H plus aqueous on both sides of the chemical equation? Looking at it, we have water, we have carbon dioxide, we have sodium ion, and we have acetate ion. I do not see H plus on the right side. So now let's look at the next one. We have the acetate ion. Do we have the acetate ion on the other side of the reaction? Yes, we do. And just like a math equation, if we have the same things on both sides, we can cancel them out. This is telling us the acetate has not changed from start to finish. It has stayed exactly the same. It's not actually doing any chemistry. All right, if we look at the next one, we have sodium ion. Do we have a sodium ion on the other side? We do again. And then the last one we have is the bicarbonate ion, which we do not have on the other side. So this tells us that that these two guys that we saw were the same on both sides. They are spectators. Meaning they're not really doing anything in this chemical equation. That's telling us if we were to swap them out with some other ion, the same reaction would still take place. So if we made it potassium bicarbonate instead, we would still expect the same reaction to happen. Or if we replace the acetate with chloride or something, again, the same thing would happen there. So the spectators can be just whatever. They're not doing anything. They're there to charge balance, and that's it. They're just kind of there to make our compounds stable. If we remove them, and just redraw what's left over, we'll get this. This is called a net ionic equation. And so this is telling us exactly what is happening in this reaction. The only things that are changing is that hydrogen ion and bicarbonate are coming together. Exactly. Just don't forget the charge on the bicarbonate there. To form water and CO2. That is the chemistry that is happening. The sodium and the acetate aren't doing any chemistry. There is no chemical change. They have not changed composition. And so those are just spectators. They're there to watch. They're there to charge balance things. That's their only purpose in this equation. So the net ionic equation will tell us exactly what is happening in a reaction. So just the chemistry that's happening. And we can do this for all sorts of things. If we did that other one before, we had this, right? This was another molecular equation we had. If we want to look at the complete ionic equation, that's when we break stuff apart. So let's go ahead and break our ions. Notice 2 sodium bromides means we have 2 sodiums and 2 bromides. Cl2 is a gas, so that is not changing. And then the bromine is going to be by itself as well. So this is a complete ionic equation. let's take a look at if anything is exactly the same on both sides. Do we have 2Na plus aqueous on both sides of the reaction? Yes, I see 2Na plus on both sides. So remember, it has to be exactly identical. Everything, the coefficient, the charge, the state of matter. Those are exactly identical, so we can get rid of them. 2Br minus AQ, we do not have that on the right side. We have Br2, which is not the same as 2Br minus. On the left side, we have Cl2. On the right, we have 2Cl minus. So those are not the same. We can't cross them out. So we have a spectator again. And if we want to do our net ionic equation, we just copy everything that's not a spectator. And so the exact chemistry that's happening here is technically we're taking electrons from bromine and giving them to chlorine. So we're making chlorine charged and we are making bromine uncharged. So we'll talk about the electron transfer process tomorrow. Or wait, today is Tuesday. Yeah, we'll talk about it tomorrow. So you'll be able to understand how these types of reactions happen. But this would be the net ionic equation here. So it's everything once the spectators are removed. So spectators must be exactly the same on both sides. And your net ionic equation is going to be everything that's left over after you cancel them out. If we swap to canvas for a second, alrighty. If we look at this double displacement reactions one for our extra practice, you're going to see that there's the net ionic and so this one calls it total ionic. It's also known as complete ionic. They're the same thing. You may want to do this as practice as well. So this will not only help you be able to pick out the spectators, it'll also help you with the states of matter and all sorts of things. So all of this, again, you'd be able to do the solubility stuff. You'd be able to do your balancing. You'd be able to then do your net ionic equations with it. And again, all of this is the answers are here. It does give you some solubility rules, but it's taking all of the 3 rules that I've given you and spreading them out into more complicated rules. So you're welcome to use this, but the 3 rules that I gave you say exactly the same thing. So yeah, don't worry. Okay, yeah, so this is there. Again, on your homepage, it's right here under extra practice. So don't forget also you have a practice quiz to make sure that Proctorio is working for you guys. Yeah, ignore the complicated rules. Totally use my rules. They will get you the right answer every time. This quiz here, make sure you give it a shot before exam day. Exam is 2 weeks. It's on the 16th of November. So make sure you do this before that. It's due November 15th. It's 1 point. It's 1 question. It's an easy question. Don't worry about the question. It's just there to make sure your computer is functioning properly and getting used to Proctorio. Also, so with the guidelines that we looked at earlier, we also have this document that has all the YouTube videos that you're going to want to watch. So there's one on safety, this is a link to a safety thing. So you would look up compounds you're using to see safety information about them. Some information about lab equipment, and then there's several techniques written out here. And then there's also a number of kind of just sample experiments. You're basically just going to be writing something like this. So they have the introduction, some lovely pictures, whatever, and then they're going to have their procedure here. Blah, blah, blah. They're doing this procedure, and then, yeah, that's stuff. Okay, hold on. We have a question. Let me switch back here. Yeah, I'll be giving you homework. Oh gosh, we're gonna get into our never-ending hyper mirror thing. Yes, you'll have homework. I'll upload that for you guys today. But yes, you would probably want to practice it anyway, just because the amount of homework I can give you is probably not going to be enough to really get this super solid in your brains. So, yeah. Okay. Alrighty, so with that, I'll see you all tomorrow. We'll talk about electron transfer reactions. Those are fun. And electronic counting. It's going to be exciting. Alrighty. Have fun.